till session 3 we looked at stack smashing, we looked at functions and calls and how stacks use function calls. Stacks are used for function calls. Now, what we will be demonstrating in session 4 is how is this function call and stack together is going to cause a vulnerability, and that vulnerability we term it as stack smashing, which was well studied in the literature. Let us look at what is stack smashing. So, just to recap, what happened when a function was called? A stack frame was created. In that stack frame there was all the local variables. So, as you see in the slide, these are basically buffers where the local variables are stored. Then there was a stack frame pointer, there was a return address and the parameters that are to be used by the called function. So, when a calling function calls the next function, first there will be parameters that are passed, that will be stored, then the return address will be stored, then there will be a stack frame pointer, and then all the there will be a buffer created for the local variables of the called function, right. So, what you see on the rightmost side are the parameters which are, this is the stack frame of a given function. So, when a function is called, whatever you see on the right hand side, from the right hand side, the parameters are the parameters for the function, then the return address, that is after execution of the function where should I go, then there is a stack frame pointer, and then there are some local variables that are stored here, right. So, this is what would be a stack frame for a given function, right. So, what happens after the function is finished? All your variables are popped, or you go to the return address that is there in the stack and then just do a return, and it will go back to the original function which was calling it, right. Now, what is this buffer overflow? So, you create something called a buffer, a character char star s is a buffer, right, where you can store lot of characters. Now, when I create a buffer where I can store lot of data elements, I put a limit for that buffer, right. So, I say 100, I can store up to 100. Suppose I cross that 100 value, sometimes you check, sometimes you do not even check. If I want to check whether for every access, so suppose I give a character array of size 256, I can store up to 256 characters there. But if I am going to violate this 256 and go for the 257, somebody has to check whether I am violating. And every time, if I say every time you are trying to access that array, check for the bounds, what will happen? The performance will take a major hit. Every time I am going to read something from that array, first I will check the bounds and then go to that, go and access that array, then the performance is going to take a major hit. So, in many of the compiled code, this is where compilers become important, they do not do this check. So, when somebody starts writing into the buffer, they will keep on writing, and sometimes they may even overshoot it and write into the next variable. So, in the memory you have defined a buffer of 256, there will be 256 bytes, say it is a character array, there will be 256 bytes, then there will be something more on top and below. So, as and when you start filling up the array and you breach the bound, then you go and write into the next variable, right. So, that is why sometimes in some of the old C programs, if you see, when I declare I have a character array and then some other integer variable following it, and so if you go and write something into the character array and if it is go above the bound, the integer variable's value will change, right. So, these are some things which you could have seen in some old compilers where strong type of bound checkings are not there, okay. Now, this vulnerability is basically exploited, right. So, what are we exploiting now? I have a stack which is provided by the architecture, I have a character array that is provided by the programming language and that is being compiled. And so there is a programming language, there is a compiler, there is an architecture, and these three together has created this infrastructure of doing function calls, correct? Do you follow? Now what I do here, I am exploiting this that particular vulnerability where the compiler does not check the bound, or the compiler does not produce an assembly code which will go and check the bounds. So what happens when the actual program is executing, one can keep writing into that buffer infinitely. So what you see on the screen is that, so the buffer is a part of the local variable of a function, and what I do, I keep on writing, so it breaches, it goes and writes into the stack frame pointer, then it goes and even corrupts the return address. And since the stack is accessible to the calling function, called function also, as a called function, if I have a buffer, I keep writing into it and nobody checks it. You got this? So by this what I have done, I have corrupted my return address. I have gone into the parameters of the other fellow also. So I could corrupt my stack, right? So this you may do it unintentionally, because your program is just trying to read a character array, and unfortunately that string is more than 256 bytes. That is an unintentional way of doing it. And what would happen if it is unintentional? Then you have some return address which will not be part of, you will go to some junk and then the program will crash, right? And that is why some unintentional bugs actually create a crash. But if I know that I could breach this buffer, can I do something intelligent here? And that is what we call as stack smashing. So what we do there? What I do is, I write a value into that buffer which is actually an assembly program, okay? And I write, so and since I can go beyond that buffer, in the return address part, as you see, I write an address that will point to the start of this code. So what I have written into the stack is an assembly code, and in that part where there is a return address, I will change that current address to point to the start of this code which is inside this buffer, okay. Now what happens when I execute a return? Which return address will come? This new return address will come, and what will happen? It will start executing the current code which I have written. So I am a calling function, I am a called function, I have access to that local variables, I keep filling up that buffer with an assembly code, right, with an assembly code of that machine, and I go to the top and I have some return address. In that return address, I go and change that return address to point to the start of my assembly code which is inside the buffer itself, right. Now I execute a return. What will happen? It will now start executing the assembly code which I have put, right. And in whose privilege? When I do a return, the privilege level will shift to the calling functions. If that calling function is a supervisor function and I am a user function, now I start executing some code, my code, with a super user privilege. Are you getting this? I start executing my code with a super user privilege. So this particular slide basically describes what I have been talking. Suppose I have a web server and it has this function char star string, and I have 126 bytes that are allocated. Now I am copying some string into this buffer, whatever that function star, that str which is an input parameter, that will copy into this buffer, right. Now which is the calling function? The calling function is this function and is calling that thing called string copy. Now string copy does not check the bounds, right. It does not check whether the length of the string str is less than or equal to 126. It does not count that, it does not check it, okay. Now what happens? Now this function comes up. Now I have when this function is invoked, a new frame is actually created with local variables in the stack, and what I do, instead of into the buffer, I write this str is writes some 126 bytes plus it will write something more, and what will be there inside that string? It will be an assembly program, and that program, the end of that program will have an address which will point to the start of this code. So, my entire assembly program along with an address which is pointing to the start of this code is available, and this I write it into the stack, and I now execute a return, and what happens? Now my code starts executing, and that code starts executing with the super user's privilege, right. And what will happen if suppose the super user is a root, and this will be a very small code, 120 bytes. What code can I do? I can spawn a shell. You know what a shell is? In your GUI you can create terminal, right, that is called a shell. Bash shell, C shell, these are all available. I can create a shell. Once I create a shell with root permission, what can't I do? Everything I can do. I can go and delete account, create accounts, you go to any user file, everything, right. And this was one of the primitive attacks. This I am in modern things there are a lot of ways by which you could avoid these things, right. Now there are solutions for this problem, but why I am talking about this problem is to basically tell you a good case study within a very small a small period of time. I have to give you a case study where there is a compiler involved, there is an application program involved, there is an architecture involved, all three things together has actually created a vulnerable scenario, right. So, I think this is one very good motivating case study to understand how this interface can create problems. Okay. Now, what will happen if I spawn a shell, right? I have a shell with root privilege, I can do a lot of things, and the thing is that once there is a facility to start executing programs with root privilege, then I can be passive, I can be active. Passive means I will just watch what you are typing, right. So, I will just keep logging your keyboard entries. It is something called a key logger. So, then I can get all your password, everything, where you are accessing, I can monitor. So, whatever you are typing, all the user inputs, if I am able to gather, then so many things I could gather. Or I can go and kill your program. Tomorrow is a conference deadline, you are my enemy, all that PDF file that are there will be erased every 15 minutes, gone, right. So, I can do this. So, these are some of the things, and I can impersonate, right. I can go into your email account and send a mail to your guide saying you are an idiot. Okay. So, these are all possible. So, one of the things that through stack smashing what they enabled what you call as virtual monitor based rootkit, right. We will virtual machine based rootkit which we will be seeing in the next session. Okay. It is called VMBR, how it is going to act, and that is going to be the real way by which this facility of stack smashing has been utilized for this. Okay. So, to sum up what we have understood in this session is before we go into VMBR is that the way the operating system, the compiler and the architecture interacts has to be understood very nicely, has to be understood with very good detail, right. You can't just have a very casual look into this, right. It has to be understood in very great detail, and if you have such an understanding, then you will be in a position to appreciate the important aspects of security, right. So, security is not something that is explicitly seen, right. It is not isolated to one entity. I do an architectural analysis, I can get lot more about security. This is not going to be possible, because security basically comes in the way by which multiple things in the system interacts. The vulnerability manifests itself because of interactions of multiple components in your system, and it is not secluded to one person, right. You are getting this. So, this is the most, that is why security becomes extremely complex. So, it is not that I have an heart attack, I have a sprain in the leg. So, it is some multi-organ failure which will kill your system, right. So, you understand. So, and that is where the complication comes, right. So, this is stack smashing, though it is a very old concept and there are lot of countermeasures for this, but I prefer to teach this in this course so that you have an understanding of how multiple things can work together. Okay. So, before we go to the next session, I will open up for questions in this session.